Just like lasers started out with very simple instruments and progressed to the point where we're doing laser comm and now even treating skin with lasers, I expect the same sort of thing might happen with gravitational waves. So much easier application than communication would be using gravitational waves as a frequency time standard. So that's going to be the thrust of the talk that I'm going to give this afternoon, at least introduce for Colby Harper, who has done a value estimation of what kind of economic value might a frequency time standard gravitational waves have. And so I'll be doing the first half of the paper, and then Colby will be doing the economic analysis. Given kind of the common background for high-frequency gravity waves, that was the original impetus to do an economic feasibility study. But the main thrust of the paper is frequency time standards. I'm going to go over briefly some navigation applications. And then in the frequency time standard applications area, I'm going to touch on how it can improve acquisition time for regular telecommunications networking, how it can improve telecommunications modulation and encoding efficiency, and how it can improve bandwidth efficiency in standard RF telecommunication systems. And then the second half of the talk will be on what kind of savings this would result in for telecom operations and what are the economic benefits of that. So this is a schematic representation of a frequency time standard arrangement. We would envision a number of extremely large gravitational wave generation stations that would create signal strength that you could pick up with remote terminals. They would propagate through the Earth with little or no impact, and so the location of these wouldn't be especially important so long as they're as spread out as possible on Earth. And the more spread out they are, the more easily you're able to triangulate to the location of the remote terminal. I envision a couple different things. I'm going to turn on my little animation here. These ground stations would also would be emitting frequency reference and would be emitting a 1 pulse per second reference. The 1 pulse per second reference would be used as a time sink, and the frequency reference could be used as a remote frequency standard so that everyone's using the same standard and you don't have crystal oscillators in every single remote terminal. This is a schematic of a remote terminal receiving a number of different gravitational wave frequency time standards. The remote terminal could triangulate its location based on the time difference of arrival of the 1 pulse per second signal from each ground station. And you could even envision a moving terminal, for instance in an aircraft, that could determine its Doppler velocity based on the Doppler shift of the frequency standards from each station, from each remote station. Conceivably, you could get by with 3 stations. I show 4 for redundancy, but you would want to pick the 3 most, the arrangement of 3 stations that are the furthest apart, so that you would get the best basis for time difference of arrival and frequency difference of arrival, so that you could determine the exact position and location of the remote terminal. It's important to determine the remote terminal location when you're in an acquisition type situation, because depending upon where you are with respect to a ground station, for instance, if you're, say, 2 miles from a cell tower, when there's an acquisition code that's being sent out from that tower, you want to search in code space to lock onto that cell tower. So when you're searching in code space, you know exactly where to search in code space if you know where your location is. It makes it more quickly achievable to achieve code sync. And likewise, if you are receiving a frequency standard, then you don't have to search through a large range of frequencies to find the signal you're looking for. You can acquire very quickly on the frequency of interest because you have an exact frequency reference. The same frequency reference that presumably the cell towers would be using. Since everybody's using the same frequency reference, there's a very small search space to run through. And so this is a way of shrinking down the frequency search space and the code search space. In addition, because the frequency standard would reduce the phase noise inside of the set, you could also shrink the phase search space. There would be much less phase noise with the good frequency reference. And so the search space would be shrunk in all three search dimensions: the code dimension, the frequency dimension, and the phase dimension. So instead of searching this entire volume, you've limited your search to a very small area. And so, for instance, where a handset, when you first power it on, might take 30 seconds to do an acquisition search before it finally achieves the signal, it could be done in milliseconds. What this really means is that the dead time when no one's talking to you and you're not talking to anyone else could conceivably just drop the link. And this link could go up and down whenever data is being transmitted. But the rest of the time, during the dead air period, you could simply drop the link and reacquire, because reacquisition is so quick that the speaker wouldn't notice that the link is dead, essentially. And so I believe this will be reflected in Colby's analysis when we get to the economic analysis as an improvement in the utilization and efficiency of the bandwidth, assuming, for instance, a 25% dead period in any given conversation. That dead period could be used by other bandwidth users. And so this is effectively a way of shrinking the utilization of bandwidth by any of the remote terminals that are using it, which represents an efficiency improvement. Another more significant efficiency improvement, if we have a good frequency reference, is the reduction of phase noise. A typical telecommunication system uses QPSK, quadrature phase shift keying, which means that if you're following as the frequency or the sine wave is circulating about the phase space from 0 to 360 degrees here, various phase positions on the circularization, as the sine wave is circulating, there are advances or drops in the frequency space, so that you're essentially encoding phase encoding the signal as it's being transmitted in one direction or another. And so for a given amount of phase noise, you can achieve given phase shift keying. If you reduce the phase noise, you can squeeze on more symbols into the same phase space. So for instance, for a high noise case like this, you wouldn't want to reduce the phase space that a symbol represents by any more than perhaps 45%. But if you have a smaller amount of phase noise, like shown in this particular figure, then you could easily encode your phase space with more symbols. So instead of using QPSK, you could go to 16 PSK, just as an example here, which improves your coding efficiency by a factor of 4. So this highlights the importance of a good frequency reference. And one of the reasons that QPSK is still used instead of 16 or 32 or higher phase shift keying is, number one, the limits of the electronics, but mostly it's the limits of the phase noise that occurs during transmission, and those phase noise that accumulates during transmission would be much less if everyone was using the same frequency standard. Likewise, in other encoding techniques that don't use phase shift keying, there are other encoding techniques such as frequency division multiple access and frequency hopping spread spectrum, in which the frequencies are used as a code. So for instance, for frequency hopping, you could create more symbols inside the same frequency space because you have much tighter frequency reference. Because the frequency reference that's being used is the gravitational wave frequency reference. And so all the RF then keys off that same frequency reference that both ends of every single link is using all the time. You can also, in an FDMA, shrink the guard bands. Because there's some frequency uncertainty between every band of frequency space, there are these guard bands that appear between the frequency assignments. We can shrink those guard bands if we know exactly what our frequencies are. And so it's easy to see that either way, with FDMA or with frequency hop spread spectrum, you can get much more bandwidth efficiency by using a frequency standard. So at this point in the paper, I'd like to turn it over to Colby Harper, which will quantify for us in economic terms what this would mean in terms of the dollar figure when you add up all these improvements.
Thank you, Gary. That a frequency time standard is valuable is clear and that it has the power to do something new. The question is, should we do the new thing? That is a question of value. To get an idea of just how valuable, we decided to look at the financial economic value of a service based on the technology. For this, we built a simple value estimation model using a discounted cash flow technique, which accounts for the time value of money at a conservative rate of 10%. Even more conservative is our approach to use low-side technical and financial assumptions throughout in order to establish a basement for our value estimation. For service-based improvements, we choose 25%. For higher density phase encoding due to phase noise improvement, we choose 200%. For frequency-based improvements, we choose 25% for an overall raw capacity improvement floor of 250%. For better beamforming due to precision positioning, we choose not to include this technology in the low side estimate, since it's somewhat speculative. For the high side estimate, 50% is used. As you can see in the table below, the low side technical improvements are on the left and the high side on the right. The high side references add up to 1,550%, and the low side references provide a model simplified multiplier of 450%. That includes 200% for cell handoff and precision quality of service improvements due to precision timing. We choose an overall value improvement of 200% here because we apply the term QoS to network usage prioritization and predictability with respect to performance parameters including delay, error rate, and throughput. These are significant improvements due to the timing and frequency standards. Even as a floor, we significantly reduce these expected low-side improvements prior to further use in our dollar valuation model to reinforce its conservative nature. These low-side multipliers play out in our subscriber-based value estimation. Applying these multipliers to a conventional high bit rate wireless market offer, conservatively for this model priced at $100 per month for 2 megabits per second, that's dedicated, unlike today. We obtain a reference MRC per subscriber low side value added due to this high frequency gravity wave FTS of $275. Note that MRC equals monthly recurring charge. This includes a 25% dollars per megabits per second discount from conventional costs due to supply increase and demand elasticity. Further, in all significant cash flows post year 2, which you'll see in the model next, we utilize a still more conservative estimate ranging from approximately 75% approximately 50% of this reference value. In the table, you can see that $100 per 2 megabits per second per month translates into $375 per 5 megabits per second per month with the multipliers applied. That's a $275 per month subscriber value add, and that alone from a subscriber basis is significant. Based on these reduced inputs, on a conservative market penetration of substantially less than 10%, and simplifying demand-supply interaction and technology refresh assumptions over a 10-year service life, we've arrived at a rough estimate of the high-frequency gravity wave FTS value floor. We estimate approximately $50 billion net present value for this service for optimization of otherwise conventional telecommunications networks. This is $50 billion that would not have existed before. It puts a number on the power to do something new. That $50 billion, by the way, is economic value that would be distributed among the various players in the market. Note that we'd be cash flow positive in year 4, and that's 4 years for mature, loud-proven technology. We're talking more about the service here rather than the underlying technology itself. While we have a significant cost drop factored into some of these assumptions already, to get a better case and worst case risk due to unforeseen circumstances, we further considered such scenarios as a drastic approximately 90% drop in costs for conventional telecommunications networks, capacity, and approximately 1,000% increase in ground station build-out and product development costs. We found that even in the face of both these drastic events, our already conservative model still manages to yield a net present value. This is favorable from a risk perspective, suggesting that even in this worst case, the service will still make money in real dollar terms. Now, $50 billion is a large number. Is it reasonable? The conservatism of our model says so. That said, we can get supporting reference valuation by switching from a bit rate to a bandwidth-oriented view. By applying the technical multiplier to bandwidth auctions and making further conservative assumptions, potentially $150 billion could be created in additional value. So we feel confident in our base model. So overall, we have the cost areas of high-frequency gravity infrastructure, which is the Earth transmitter station cost, the remote terminal receiver overhead. We had savings areas for the TDMA efficiency, the PSK efficiency, and the FDMA efficiency. And we can conclude that assuming the eventual development of high-frequency gravity wave technology, the benefit of this technology to Telecom is easily quantified. This predicted savings to Telecom exceeds $50 billion in present value, and we view our value estimation as sufficiently conservative, supportable, and transparent to merit serious ongoing dialogue regarding commercialization of such a technology. Thank you.
We have about 10 minutes for questions.
Colby, that 150 million, is that for 10 years?
The 150 million is a supporting reference valuation, so sort of like getting an appraisal on a house. We went to another view to see if our base model was reasonable. So our base model is 50 billion over 10 years.
Yeah.
But the 150 billion is to check if our numbers make sense in another way.
So you're saying you can make, the value would go from 50 to 150 billion?
Yeah, we would view that as a ceiling.
Wow.
Even though that alone was conservative because we didn't count all the megahertz that's available on the globe, and we didn't count all the pops that are available, for instance, China and India, as they come online.
In simplify this thing for me, what you have is a time standard. How accurate is it compared to present time standards, and why should I throw in my present time standard or GPS system or whatever else?
The GPS has certain limits. For instance, it's a low Earth orbit system. And so there's always going to be the Doppler velocity that enters into the standard. And so it's hard to put an upper limit on how much better it is, but it's easily,
Well, let's say I have a cesium clock. Why should, if I can sync my cesium clock with somebody on the other side of the world, why do I need your system?
The cesium clock is not really, well, this system would probably be tied, for instance, to something at the Naval Observatory, and they run off a series of cesium clocks. The cesium clock is an expensive clock, and not everybody has that cesium clock. This system would supply that Naval Observatory cesium clock set to all of the users directly. And so the limit on the system wouldn't be the transmission of the frequency time standard, it would be the actual frequency time standard. So it would be like everybody had a cesium clock.
Okay.
Everybody had the same cesium clock.
Within the accuracy of what a cesium clock has.
Yes, of course. You can't improve,
All right.
on the cesium clock itself.
Yeah, Bob?
Two questions. One is, again, what precisely is the difference between using high-frequency gravitational waves and our current system? What is fundamentally the difference between the two approaches?
It's that the gravitational wave propagates undisturbed. That's really it. And that everybody can use the same standard.
Okay, so there's no reduction in the time between transmission and reception that we now find in.
It's going to have the same delay times, but you'll be able to measure the delay times very efficiently at the remote terminal, assuming that the remote terminal can determine its location.
Okay, the second question is, if, in this case, if you're going to get, say, $51 billion over 10 years, you could probably go to a angels group and eventually venture capitalists. Is there some backup position with the technology not fully matured that they might get an earlier payoff?
Well, yeah, certainly. And I don't like to put that in the briefing because then I run into export restrictions and so on. But obviously this would have value from a strategic comm point of view because you could bury all the receivers and transmitters, and they're very survivable. The other aspect of this is if you're the only ones with gravitational wave transmitters and receivers, then it's low probability of intercept.
What, would there be a cash value to that?
It depends upon whether the Defense Department sees value in it. Presumably, they would see value in it, and so it's whatever cash value they would be willing to assign to it. For instance, a development contract to replace the existing Minuteman communication system would be one conceivable system, which would be in the several $100 million range.
We did find that when we looked at more central node operations, an initial quicker rollout, that the net present value is still in the billions and nearing $10 billion. Gentlemen, over there.
Have you done the calculation to quantify the RMS temporal stability of your frequency standard?
It's limited by the cesium clock, not by the gravitational wave.
I'm just wondering, for communications applications, not so much the time standard, what do you think the value of the licenses would be for bandwidth, for spectrum, given that it would maybe hypothetically double your existing spectrum?
Yeah, this particular application wouldn't require very much bandwidth. You could squeeze it into a very narrow bandwidth somewhere, but obviously the gravitational wave bandwidth is not assigned right now. So, once the technology is established and becomes more usable, then you could conceive of an entire parallel bandwidth. And so at that point, obviously the bandwidth would cut into the bandwidth of the value of the current bandwidth, but it would take on its own value. I wouldn't have a tough time necessarily. I don't know how you would.
I'm just kind of curious how you mechanize this. You're suggesting a company in the U.S. might do it, you're going global, you're going to rent out portions to foreign countries? Or
I would think it would have to be global enterprise in order to get
initially?
a return. It's by nature of gravitational waves global because it's going to go everywhere. Bob talks about the dumbbell shape, but obviously for this application you would want to create a broad coverage, global coverage at each transmitter to make sure you have uniform coverage, which means that it's going to be by nature the serviceable.
It would seem to me that you're going to need some correction for two things at least. One would be earthquakes or truck driving by. The other would be you need ephemeral corrections for sun-moon distances that might affect the gravitational wave. Is that true?
Yeah, I'm sure that's true. I haven't considered any of those low frequency corrections.
Is this applicable? Let's take this much larger in terms of gravitational wave. Would this be the basis? Could this be the basis for a solar system GPS?
I don't see why not. Otherwise, why I presented at this conference? But yeah, the propagation favors distance. So in a case like that, you would want to tune the radiation pattern more tightly.
And Dr. we have one.
Do you expect to distort the electromagnetic communication with gravitational waves?
Could you restate the
Do you
question?
expect some distortion? Some
No, it shouldn't. It's very, very tiny. We're talking about 10 to the minus 30th type signals.
So you're using an extra dimension.
It's a strain dimension. It's delta meters per meter. And it's quadrupole radiation, but it's very, very tiny amplitude quadrupole radiation. And it's going to be difficult to miniaturize the receivers. The transmitters are just so hard. That's why we took this application first. We're just going to leave the transmitters big.
Do you think that people could use this time standard, as Bob alluded to in his earlier presentation, and perhaps use polarization shifts to measure things within the Earth, like hunting for oil reserves or what have you?
Yeah, I haven't studied the impact of polarization shift other than to realize that it's so small it wouldn't impact the frequency time standard usefulness here. It's well below receiver and transmitter phase noise, and so long as it's down inside of our phase noise, then from a frequency time standard point of view, it's negligible compared with phase noise inherent to the electronics.
Time for one more question. Okay, let's thank our speakers.